Okay, so last time we were talking about flux integrals, which are an application of the surface integral of a scalar function. So just as a quick reminder, if we were talking about the surface integral of a scalar function, that would be something that looks like this, where our surface is z equals g of x and y. But if you look back to 16.7 part 1, we also did look at that from the other perspectives. Okay, so go back and review that. And the way that we worked one of these integrals is we put everything in terms of the independent variables. So in this case would be x and y. So for z, we put in f of x and y. And for ds, we put in the square root of gx squared plus gy squared plus 1 dA over d. This is not a surface integral anymore. This is d. And that is where d is the projection in the independent variables plane. So in this case, in the xy plane. So that's what we did way back. That was 16.7 part 1. Then last time what we talked about is an application of this, and the application was called flux. And officially what we're doing is we're taking f and dot it with the unit normals ds. But the shortcut we found, depending on if we chose n in the appropriate way, the unit normals, if we choose n the following way, where we have the surface and we write it as z as a function of x and y, and then we get everything on one side, and we call this function here capital G of x and y and z, then the shortcut is going to be if we take f and we dot it with the gradient of capital G dA. Now, just like on the problems up here, there were other orientations. And if we're going to be doing another orientation with different independent or dependent variable, then this will change accordingly. Okay. We did talk also about the orientation of n. We're going to choose an orientation in a agreed upon way so that we know which direction is for positive flux and which is for negative. All right, so in your homework from this section, you had this problem here. F is x plus 2y plus 3z, and the surface is this unit cube. Now I say unit cube, but it's actually 2 units on each side. It's 1 in each direction. Okay. And so if we were going to do this, if we were going to find the flux out of this, first of all, it is a closed surface. And so for a closed surface, positive orientation is outward. So on this closed surface, we have outward orientation, which on the top means upward, on the right means rightward, left means leftward, and so on. Okay, outward orientation. And so the way that you should have done this on your homework is we break it down into each of the 6 surfaces. So for instance, on the front surface, let's do the top surface first. Top surface has the equation z equals 1. So that would be z minus 1 equals 0. And so this is our capital G. We would need the gradient of G, which is 0, 0, 1. That's where I typically look. Do I really want 0, 0, 1? Do I want upward there? Yes. So we're good there. We take our F and we put F in terms of the independent variables. So in this case, you can't have the Z here. So we put in our surface. Our surface is z equals 1 here. So the surface is z equals 1. That will go here. And so our f is x to y 3 times 1. And so when we take the dot product, We take the dot product of f and that gradient, we're going to get 0, 0, 3. We're going to get 3 dA over d, where d is the projection in the xy plane. So in the xy plane, d is, whoops, from -1 to 1. Okay. And so the shortcut way of doing that integral is this just going to be 3 times the area of that square. And that square is 2 units on each side. So we would get 12. 12. I said 12 and I wrote 14. Okay. Then we work, let me go ahead and work the bottom here. So when we're working the bottom, the equation of that surface is z equals -1. And so we get everything on one side, and this is what we call our g, and our gradient of g is 0, 0, 1. But in this case, on the bottom surface, we want outward unit normals, which means downward. So in this case, I actually need the opposite because I want downward. Our f is x, 2y, 3z, but in this case, z is -1. Whoops, z is -1. And so here we have a -1. And so when we take the dot product this time of f dotted with the gradient, opposite the gradient, we're going to get 3 again. The projection in the XYZ plane is the same region, and so this is going to again be 3 times the area, which is going to give me a 12. Okay, let's look at the front face. The front face has the equation x equals 1. So now this time x is our dependent variable. And so our g is here. And our gradient of g is 1, 0, 0, which would be pointing directly out towards you here. And that's what we would want for the outward unit normals here. We would want the one that points frontward. And so that's what we need for that one. Our f is x, 2y, 3z, but we're going to put in our surface, which is this time x equals 1. So our surface this time is x equals 1, and so our f is going to be x, which is 1, 2y, 3z. And so that dot product is going to be 1 dA. The projection is in the YZ plane this time, but it is the same square. If I project in the YZ plane, it's still the same square, and so we're going to have 1 times the area of that square, which is going to be 4. The back is x equals -1. So that means x plus 1 equals 0. This is our g. Our gradient of g would be 0, 0, 1. But if I look and see on this back surface here, the one that is parallel to the YZ plane, that back surface, an outward unit normal there would be backward in the negative x direction. So we want, in this case, I made a mistake there, a minus. This should have been a 1 here. So 1, 0, 0, and then I'm going to multiply by -1 because I want the backward unit normal. My f this time, substituting for x in my f here, x this time is -1. So this is -1 and 2y and 3z. And if I take the dot product with f and negative the gradient, -1 times -1, I will get a +1 with the same projection, and so that's going to be a 4 there. Okay, the right side. The right side has the equation y equals 1. And so we're going to get that y minus 1 equals 0 is g. This is our g. And our gradient of g is 0, 1, 0. And we do want the right facing normals on that right side, so that's what we want there. Our f, we go back to our f and we put in this time for y equals 1. And so we'll get x, 2, 3, z. And when we take that dot product, we get 2. The projection is still that square of length 2 on each side. And so this is going to be 2 times the area. So 2 times 4, which is 8. And then the left side, I think you see where this is going. But on the left side, the equation of that surface is y equals -1 or y plus 1 equals 0. That's our g. So the gradient of g is 0, 1, 0. On this left side, though, we want our positive orientation. We want n to be chosen outward. So outward on the left side is leftward. So that should have a negative y component. And so I want minus the gradient of g. Our f is x and then y, or 2 times y. This time y is -1. So 2 times y is -2. Whoops, -2. And 3z. And so that dot product here is 0, +2, 0. So 2 dA. And so that's going to be 2 times the area, so 8. All right, and so the flux, the total flux out of this surface is to add all those up. And so if you add all those up, you'll get 48. What we're going to consider in this section is a tool that will allow us to compute flux in the special case that we have a closed surface. So it can apply to the problem we just did. And here's what it says. It says if you have a simple solid region, and S is the boundary of your surface, so that means we have a closed surface, and this theorem presumes outward or positive orientation. Here's what it says. This, which is the flux, can be computed by a triple integral of the divergence of F. Okay, how does that work again? The divergence of F, remember, is, it is, if you like that shorthand notation, it was del dot F. It was the partial of the first component with respect to x, second component with respect to y, and third component with respect to z. So if I apply that on the problem we just did, our f was x, 2y, 3z. So the divergence of f is the partial of the x component with respect to x, partial of the y component with respect to y, and partial of the z component with respect to z. So the divergence of f is 6. And so for the last problem that we just did, the flux, which we broke into 6 pieces, we could do this instead as the triple integral of the divergence of f over our solid, where our solid was that cube. Okay? Now, you know how to set up that triple integral, but in this case, this is 6 times the triple integral of 1 dv. So a shortcut way of doing that triple integral is 6 times the volume of that cube. That cube is 2 units per side, so that's 2 times 2 times 2. 8 times 6, 48. Much quicker than the way we just did it. Okay, now the proof, again, this is more something you're going to do in an advanced calculus class, but here's a really rough idea of what's happening. Remember, when we're looking for a surface integral, so we're essentially looking for the rate of flow through this closed surface, and we're measuring going outwards. Physically, what we said the divergence of a vector field is that at every point in that vector field, you're measuring, when you're measuring the divergence, you're measuring the net flow. Is it going out of each point or into each point? So you could kind of see that if we took all those individual divergences and added them up, that it would be related to the flow in and the total flow in and out of that surface. Now that's not a proof. That just gives you a rough idea of why would it be that a triple integral would be related to a flux integral. The triple integral is essentially summing up all the flux, all the net flux. Okay? All right. When can I use it? Closed surface, outward orientation. So this problem here, this next example, we did this last time. And if you look back, you might recall, we had this plane, and then it was closed. So bottom, left wall, back wall, and we did 4 separate surfaces. The shortcut for this now, because we have the divergence theorem, is the flux would be the triple integral of the divergence and the divergence of this vector field partial with respect to x, partial of this component with respect to x, that's 0. And divergence is not a vector. So partial with respect to x of the x component, partial with respect to y here. So that's going to be 0. And partial with respect to z here, which will be 1. So the divergence is 1. And so we just have the triple integral of 1 dv. Okay, now in this case, that would just be the volume of this tetrahedron. If you happen to know the formula of that, I'm going to guess that many of you don't. So we'll go ahead and do it as a triple integral. But you're not always going to get a constant here. So we don't always get that volume shortcut anyway. We're going to have to remember our triple integrals. So in this case, that dv, I have lots of choices for the order I want to go. But in this case, both the integrand and the solid look equally easy in any order. So I would just go ahead and set this up as dz dy dx So z goes from 0 to the plane. So here's the plane. I'm going to solve for z. I'm going to get 8 minus 4x minus 2y. And then the projection in the xy plane is here. The projection in the xy plane, y equals 4, x equals 2. Or you can get it from putting in z equals 0 there. So 4x plus 2y. 4x plus 2y equals 8. And so if we solve for y there, y equals 8 minus 4x over 2. Okay, so the limits for dy dx, y would go from 0 to 4 minus 2x as x goes from 0 to 2. So you could compute that as a triple integral. So that's the gist of the divergence theorem. It's a tool for helping us compute flux out of a closed surface. Okay?